Okay, so hello everyone. Myself Prakash, Assistant Professor from Mechanical Engineering Department, Tyagaraja College of Engineering, Madurai, Tamil Nadu. So I am welcoming you all for my video presentation on how I planned virtual lab for my own course, non-traditional machining process. The course code is 22MEPM0. The target audience are BE Mechanical Engineering 6 semester students. So this course we have a 6 course outcome. On successful completion of this course, students will be able to explain the characteristic, select suitable mechanical process, thermoelectric process, chemical, electrochemical, as well as high energy machining process. For this assignment, I consider CO5. So the Bloom's level TPS, it stands for Tyagaraja Proficiency Scale. In our institution, we follow this scale. So my assignment on virtual lab, the planning. So I selected the topic called electrochemical machining process. The course name is non-traditional machining process. I planning to cover the course outcome 5, explain the electrochemical energy-based machining process. Electrochemical machining process, it's a non-traditional machining process for hard and conductive materials. The identify the suitable simulation or virtual lab. So frankly speaking, I I tried a virtual lab for my own course, but I didn't find. But once I search all those things, I find this web portal. Virtual Lab platform is a micro machining lab. It is designed by Indian Institute of Technology, Delhi. So this is the link for that micro machining lab. So it is an initiative of Ministry of Education, Government of India, under the aegis of Nation Mission Education through Information and Communication through NMEICTE. For this for this IUC course only, I got to know that this lab we have. Previously, never used, but this time I used because of this assignment. So this is a screenshot, a micro machining lab. This is a platform. Again, the micro machining lab. If you click this list of experiments, it shows 8 experiments. All the experiments are related to non-traditional machining process. Currently, I'm handling this course. And if we click this electrochemical machining, experiment number 7, so you may find this web page. So this is the link for my virtual lab, study of electrochemical machining process. So if you click this simulation, you find you may go to this simulation where it shows industrial electrical machines. So lab manual. So this is a not a traditional lab. This lab is designed for my own course. So theoretically, I explain what is meant by electrochemical machining, but this virtual lab it shows how the workings are going. So I prepare the lab manual based on our input PDF file. So topic is study of electrochemical machining process. The principle is electrochemical machining is based on the Faraday's law of electrolysis. The workpiece acts as anode and tool acts as a cathode. A high current, low voltage deep current passes through an electrolyte flowing rapidly between them. It dissolving metal ions from the workpiece. This is a basic process. So if you supply the electricity, the metals are removed by means of dissolving metal ions. This process is ideal for machining hard, complex shapes without tool wear or thermal damages. What's the objective? The objective is to understand the operating principles of electrochemical machining, and it is used to observe the effect of current and material properties on metal removal rate. It is also used to calculate MRR using Faraday's equations. Okay, what's the instruction? So I said earlier, I pass on this URL to my students. I insisted them to click the simulation link and ensure the industrial electromachining page diagram is visible. So this is the screen. This is the experiment. If I click this simulation, this window will open. So where this is a industrial electrochemical machining machine where you may select your metal. So what kind of workpiece we are going to machine, and the atomic weight is defaultly it will come. And if you choose valency, you may find the removal rate in terms of gram per second or 10 power 6 meter cube per second, right? And one of the assumption is it is a 100 ampere, right? So where this screen will appear, and you may select what kind of metal. If you click this select drop down, it shows some various metals here. So you may choose which kind of material you want. So for example, if you assume aluminum, it automatically calculate the atomic weight. So here I choose aluminum, and the atomic weight also calculated. If I choose valence, there are three options, three, two, one. If you click this, and then you need to set the parameter as a default, the current value of 1000 ampere and 100% current efficiency. So if you click the removal rate, which unit you want. For example, if you click gram per second, it shows some value, what shows value, and a 10 per 6 meter cube second, it shows another value. So again, repeat the steps to for different material and find the various MRR for our workpiece material. So again, it has another feature called the simulation. So if you click this power supply, it will automatically visualize, it will automatically simulate this process. So how the electrolytes are flowing and how the metal removes are take place. Again, this will help students to learn how the working going on, and you may compare how atomic weight and valence influence the MRR. So this is a very, very interesting and a very informative web page portal. So for this manual, I prepared a few sample questions. One is which of the following law for fundamental principle of ECM? As I said earlier, it's a Faraday's law. And in ECM setup, the work is considered as the anode, tool is considered as a cathode. Again, if you double the current in ECM process, what happens to metal demolition according to the Faraday's law? Again, it doubles. So it is directly proportional to MRR is directly proportional to ECM. The positives are the biggest part is positive is accessibility. The electrochemical machine is very expensive. It is very difficult to experiment, and it is also look very dangerous and hazardous, and often a black box in a physical lab. So this simulation allows every student to safely operate the process, and it visually connects Faraday's law to real-time MRR calculation, which helps demystify the theory. So this is one of the important positive for this virtual lab. As M.A. Nickerson review highlight, this kind of simulation bridges abstract concepts like ionic dissolution to tangential output. The step-by-step material of action and the parameter adjustment promote inquiry-based learning and keep students engaged. Right? So shortcomings. So I found some difficulties. However, the simulation has a clear limitations. It's quite basics. It doesn't visualize the electrolyte flow, gap with the dynamics or the evolving shape of the workpiece. Again, it has some simulation, but it won't show how the workpiece are changing, and it assumes 100% current efficiency, which is generally it is unrealistic one. So some students found that interface outdated and lack of dynamic animations unmotivating compared to the modern PhD simulations. But impact on learning, despite these flaws, it promoted learning. Students could easily see how material properties, atomic weight, valency affects the MRR. The structured quiz confirms the grasps the core principles. That is, it is used to ensure whether the students learned or not. Participation was very high because they could experiment without the fear of breaking expensive. So overall, it has some flaws, but it is one of the best initiative in our Indian government. So future improvement, I am planning to do in other non-traditional machining process. So I will pair the simulation with a short video showing the real ECM machine in actions and a guided worksheet asking students to calculate theoretical MR and compare with the simulation output. Use a simulation as a pre-lab activity before physical demonstration, not as a replacement. Right. So this is some of the future improvement. Overall, the final conclusion is it's a useful tool for conceptual understanding, but it works best as part of the blended learning strategy. So thank you all. Thank you for your time.